SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. Let's continue our discussion. So this is of the two-dimensional solid mechanics. We have derived all the weak form of the weighted residual statement, and then where the displacement UV has been expressed in terms of the nodal values. So here we have taken the triangular element with 3 nodes, and then substituting all those things. So the equations here will come out as the 2 equations are now put as in the matrix form. So it's Ki, each of these submatrices are 2 by 2 matrices, and Ui, Vi, Uj, Vj, Uk, Vk. So this is a set of 2 equations in the x direction and y direction corresponding to the weighting function being the trial function of ith node. And in that context, so we have the left side here, right side, which is the nodal values. So these things are coming because of the force, that is the body force, and the traction vector on the traction boundary condition, gamma q or gamma t. Sometimes, please excuse me for writing it as gamma q, gamma t. So both are taken to be synonymous. Okay, they're taken to be equal. So all right. So now the integral evaluation Ni on the body forces. So we know that it is Ni x bar, and the second component is Ni y bar. So if you integrate it, then it will become Ni integral over the area will become area over 3, and that's what we have written. And here, of course, we are assuming that these body forces x and y are constant over the element. That leaves you now just another small component here. So which so there are 2 types of situations, either the element being very much inside or element being a part of the element falling on falling on the traction boundary condition. So we know that whenever the element is very much interior or inside, then the shape functions corresponding to these nodes on gamma q will be 0, because the Ni here will be just non-zero over this element, and by the time it comes here, it is 0 everywhere else. Outside this, it is going to be 0. And so, however, if you have the element right on the boundary, like this situation where you have one internal node I inside, and then again here, the shape function corresponding to this node I, Ni, is going to be 0 on this. So its contribution is going to be 0. If the element edge Jk falls on this traction boundary condition, so we know that the Nj here is having a value of 1 here and goes to 0 linearly to k. So its integral along this side will be simply sjk by 2. So sjk is the side length, and then if you integrate, they linearly varying to 0. So then if you integrate it, it becomes half. So similarly for this one. So the contribution of nodes for interior element will be 0, because Ni will be 0 on gamma q, while if the element falls on gamma q, say here jk on gamma q, then integral nj on gamma q is, say here, it will be sjk by 2. So thus the contribution will be thus fjx and fjy will be simply tx sjk by 2 and tv. So that's why you observe this one. So this contribution only comes into the picture only for the elements which are there on the traction boundary condition. So even for this element, this node is interior away from the boundary. So its contribution of this node will be 0, 0, 0. Whereas for node J, so if it has to be integrated along the traction boundary, that's along Jk, for example, so then its integral will be sjk by 2. And so exactly the same thing is true for the node K. So its integration along the traction boundary will be sjk by 2 again, right? So that way, so this is a boundary condition which comes into the picture only for those elements which are having sites on the traction boundary. Okay, so thus we have the contribution of this one here is to be taken carefully as necessary. So that's what we have here, is that putting it concisely. So the equation with weighting function value I being equal to Ni so this is what we have done just now. So this is nothing but we have Kii, right, multiplied by Uivi, Kij, Pj, and then on this side we have fi x, fi. So these are the nodal loads. So this is for the element E, a general element with weighting functions taking to be Ni 0. So for weighting function Nj, so this is corresponding to the jth node. So what will we get? So just we can generalize it. We get, what is that? So it is Kji, right? And Kjj, okay. Okay, so this is the second set of equations. So each set of equations, this is equivalent to 2 equations. Each one of them is 2 by 2 and so on. And finally, taking weighting function as Nk and Nk, we get what do we get here? Exactly the same thing, K, Ki, right? So this exactly follows the same procedure as heat conduction, except that here each node has 2 variables. Okay, so this is another equation. So like this, so we have 2, 2, 2, 2. In fact, the whole for the whole element, so we can combine all these things as like this. Ai, okay, Ai, right? And okay, so like this, so we can put all of them together. Jx is Jy. Okay, so this is for the element. So this is the final set of equations where if you look at the size of this element K, so each is a 2 by 2, 2 by 2, 2 by 2, 2 by 2. And so that way the whole thing becomes a 6 by 6 matrix. And then this component 6 and this component is 6 and 6 by 6. And so each node here has two variables, displacements in x and y. Okay, so this is the final set of equations, and so each is a 2 by 2. So just for the sake of completeness here, so let us, we have derived this one. We gave Kij, you recall. So this is nothing but a B matrix and a D, and we have it in terms of Bi 0, 0, Ci and Ci Pi. So that's what's being written here times area. So where Pi is nothing but okay, right? So again, in the concise form, if you go back and see the equations for B, so this is what it is here in terms of J, and this is here in terms of transpose, and then this A is the area of the triangle. So if you want to, just for the sake of completeness, so let's write this one. It's a 2 by 2 matrix. So we'll write it as D11 Bi Bj plus D66 Ci Cj D12 Bi Cj plus D66 Ci. So it is D21 Bi Bjcl D66 Bilm D22 ClCm Cij all right. So this is a 2 by 2 matrix of Kij in terms of Ij, and this, the indices can be replaced by Ii, Ij, Ik, and then you will get different D this K matrix here. Okay, so that's we have this 6 by 6 matrix, and then this is the 6 things 6 components of the displacements followed by 6 nodal forces. So we have one element, and these things obviously go to the degrees or the nodal degrees of freedom I, j, k. Each node has 2 degrees of freedom, and depending upon the node numbering, so you have to assemble this, and then you have to apply the boundary conditions. So we will apply the boundary conditions and all that. We know it, and then we'll come to that by giving a numerical example a little later. Okay. So this is the approach here is a very generalized approach based on method of weighted residuals, given the governing equation in terms of differential equations. So two equations are given here, and then we have to deal with them simultaneously. In fact, you can even extend this for more number of variables. Like in fluid mechanics, you will have 2 velocity components and a pressure component coming from Navier-Stokes, and then you have to deal with 3 nodal variables for each node, and then you have 3 governing equations. So this definitely gives you a complete picture how we have to take care of the governing equations and the 3 governing equations to be taken simultaneously, as well as the 3 nodal variables. Okay. So now what we do here is that we will see another appealing approach, okay, based on the variational formulation. Okay, the same solid mechanics continuing. So we will look at the second approach based on using variational approach or variational method. So what is this variational method? So solid mechanics using the variational methods. So we will try to derive the finite element equations. Okay. So earlier it was based on the method of weighted residuals, and obviously the method which we used was the Galeckin approach, where we took the weighting function same as the trial functions. All right. Now what we do here is that we would like to do this 2 dimension, which can be extended to 3 dimensions. So in this variational approach, we will apply the minimum potential energy principle. This we mentioned when we talked about the Rayleigh-Ridge formulations and so on, where we took the exactly the same thing in the case of one-dimensional problems, where we derived the potential energy, right? And then we minimized it with respect to the unknown variables. All right. So what is the minimum potential energy principle? So minimum potential energy principle is that we have to find out the potential. So here the potential energy is consisting of the internal energy, internal here elastic energy, and then work of so this is also we mentioned at that time. So this internal energy is due to the elastic deformations, and then we also have external forces like this traction acting on the surface, as well as the body forces which are acting everywhere in the body, right? So this is what we have to find out to start with, the potential, and then this potential will be in terms of obviously the displacements. This is a deformable body, so the displacements here of various points, and then they will contribute to internal energy as well as the external work done. So the principle says that the point of equilibrium, the energy here, the potential energy that is there in the body as a whole will assume a minimum value, right? And that minimum value is of course subjected to certain boundary conditions. So what we say here is also in another another statement is that out of all the possible displacements here, the one set of displacements which minimizes the potential energy is the solution. Is the solution in the sense that the problem can also be posed as in the form of differential equation. So that means that it is also going to satisfy the governing differential equation. Or it is also another kind of statement is that the solution for the governing equation in the form of differential equation is the one which is going to minimize this potential energy. So you can state it in any manner, and both have their own advantages. And the one here, this one is a very classical principle which has been there for centuries, and then this is also very appealing. So then once we do this potential energy and then minimizing it, it's a very straightforward and simple procedure. This is a very appealing, and then from many other contests. So we will see that from other contests also a little later. So what is the internal energy here? The internal elastic energy here So the internal elastic energy here is due to the elastic deformation. So we are assuming that body is linearly elastic, and then as the body gets deformed, so the internal energy is generated in that and then formed, and then that is the one going to depend upon the stress and strain to which a particular volume is subjected to. So the elastic energy here is, so here we call it as energy density. U here is stress multiplied by strain just giving a little bit more space here. So what we have here is that the strain energy within the body is a multiplication of this stress and the strain, the components here x, and then there is a normal strain y, the normal strain z, and then these are the shear strain components. So each shear strain is multiplied with the corresponding shear stress. So there is the shear stress and shear strain. So that way there are 6 stresses here, and then the corresponding strains. Okay, so this epsilon x, epsilon y, and all those things are the strain components. Okay, so this is this is the density, right, of strain energy density. And then, of course, there is a half here, because when you start loading it from the zeroth state, so then by the time you come to this final state, so then there is a half here because it's linearly behaving solid. So this is the, and then you this is energy density at any point, and then you integrate it with volume. So here we are using dV, otherwise we could have used omega also. Okay, so then the other term, work of external forces. So the external forces here, the body forces is x bar So these are three components, x bar I in the x direction and y direction and z direction. So this is, and then, so then if you want to find out external forces, you have to take these body forces and multiply with displacement. So here the displacement is okay. So the work is equal to then x bar u, y bar v, and again and this is work of external forces, and this is, and remember that when it goes into the potential energy formulation, so the contribution of this one is taken with a negative sign here. So this also we explained sometime back. Okay, so like this now pi is, so the total pi so whatever is there, we are just repeating it here. Okay, so this is the total potential due to the internal energy, and then this is the work of external force. There is also another external force that comes into the picture, is the force acting on the traction boundary here. So that also we have to take into consideration. So it will be very similar to this one. So that term also we have to put here, and then we'll have to continue how the whole thing can be written in terms of displacements. Okay, I think we'll stop it here and we'll continue it in the next class. So we'll start from this point and we'll continue. Okay.